Okay, here's my plan for the final lecture. I want to briefly remind you what we did before, mainly the previous lecture. I'll just recap a little bit. And then I want to tell you about something that I term finite width corrections. So you might recall before we studied neural networks at infinite width. And somehow the whole point of the lecture today is that infinite width is nice mathematically. You can say a lot, at least in the limit we studied last time. But for a variety of reasons, it's kind of too simple-minded to capture behaviors we care about. And in particular, I'll try to explain that you can't understand the effect that depth has. They call it deep learning for a reason. The networks you have are deep until you study things at finite width. Depth and width are not independent of each other. That's going to be, in some sense, the main theme. But let me first recall what's going on. Okay, so again, we're going to consider a random fully connected network. The network, I'm going to remind you of the notation. All right, so here I go. I have two things. So first, let me just remind you of the notation for how we passed inputs through the network, right? So X was an n0 dimensional input. And at layer little l plus 1, it gives you an n l plus 1 dimensional vector, and I is the component of this vector, right? And the forward propagation equations were just recursive in L. Like they look like this. It's just an affine transformation of what you compute at the previous layer. Ij sigma CLJ x. Okay, so if you want to be very precise, right, little l runs from 1 up to capital L, and little I runs from 1 up to n sub little l plus 1. That was the notation for the depth. That was capital L, and n sub little l plus 1 was the width of our layers. Okay, so that was just the generic forward pass in a fully connected network. And what I meant by random is at the start of training, which is typically done like this. And so the W's are independent Gaussians with some mean 0, and the variance is a constant CW divided by the width of the previous layer. That's just to keep these matrices of weights in each layer having reasonable singular values. That's the usual kind of random matrix theory initialization. Okay, and then the biases we just take to be Gaussian, mean 0, variance CB. CW and CB are just order 1 constants. And depending on how much time I have today, I might tell you about what's called tuning to criticality. It's how to choose CB and CW so that at large values of the depth, you still get a reasonable, kind of random neural network at the start of training. Okay, so I don't know if we'll have time for it, but you might get there. Okay, so what did we do before? In the previous lectures, we basically studied, well, first these random neural networks, and then at infinite width, we trained them. And what did we find? We basically found the following. So when capital L is fixed, and we took the hidden layer widths n1 up to nl to infinity, we saw things which are either great or terrible, or maybe great and terrible, depending on your point of view. Right, so the first thing we saw is that although this looks like a very complicated stochastic process, right? This is a random function of the input x. It actually becomes very simple in this regime. We just got a Gaussian process. So what did we find? We found that the process of outputs, and I'll write it CL capital L plus 1 of dot. So it's a random function. So maybe I should say fixed. And n0 and n plus 1 fixed. So we fix the input dimension. We fix the output dimension. Fix the depth. We'd send the widths to infinity. Now you have some random functions. You get a Gaussian process. So this converged to a very simple-minded thing. It was the Gaussian process with mean 0. And all of the components in the final output layer, which has dimension n capital L plus 1, were just independent. Okay, they had a certain covariance function KL plus 1. That was my notation. And this was my notation for saying that each component is just an IID draw from the same Gaussian process. Okay, and in fact, we derived a recursion for the covariance function KL plus 1 evaluated at 2 network inputs. That's all I have to do, right? This is a thing that tells me about the covariance between what happens when I plug in one x and another x. And the formula was very simple. It was CB plus CW times the expectation with respect to the previous Gaussian process, KL, of what happens if you apply sigma, your nonlinearity, to, let's say, the first activation at x1 and the first one at x2. I'm calling xi. Okay, so this was like the first half of the previous lecture, the Gaussian process limit, very beautiful. And so neural networks seem nonlinear and they become Gaussian. So it's good or bad, depending on whether you like Gaussian processes. Okay, but we saw more. We saw another very important fact. We saw that if we start from this initialization and we actually train by gradient descent, or more precisely, I said gradient flow, we saw that with a small step size, small, or really we thought infinitesimal step size, doesn't matter, step size, a gradient flow, maybe let me say it this way, we can replace this fully nonlinear network, which seems complicated. Remember, maybe I'll put the notation here. Sometimes I remember that it's a function of its parameters. So this theta here is just the collection of all the weights and biases, right? We can replace the full nonlinear function ZL plus 1 of x and theta by simply its linearization at the start of training. Okay, ZL plus 1 of x and theta 0. So theta 0 means you choose the w's and b's at random. That's how you initialize your optimization procedure. Okay, plus the gradient with respect to theta of ZL plus 1 x theta 0 times just the first order difference between theta and theta 0, and that's it. So it looks complicated, but you see all the complication is really in this term here. This is the behavior of the Jacobian at the start of training, and otherwise it's simply a linear model. Okay, so this is amazing. We can make this replacement when we do gradient flow, okay, gradient descent on a loss that looks like L of theta is maybe the sum on I goes from 1 up to the number of training data points you have of, let's say, some squares of some differences in predictions. Okay, z of xi theta minus yi. Okay, so what I'm trying to say over and over is that in this infinite width limit, in the sense that the depth is fixed and the hidden layer widths all go to infinity, neural networks become unbelievably simple in this regime. At initialization, they're Gaussian processes. For the purposes of training, at least on these kind of losses, they become linear models. Done. That's a beautiful thing. But here's really the problem. Okay, this is where people become very unhappy, so I'm going to put a frowning face. Okay, so the issue is that, well, a linear model can't possibly learn any features. You fix the basis of features, which if you want, you can just think of as like the eigenvectors of this Jacobian. And you're just learning a linear combination of those eigenvectors. Okay, so there's no feature learning. No feature learning is possible in this setting. And in some sense, in practice, the most important thing neural networks do is they learn features. Okay, so unlike this linearization, what typically happens in practice is your Jacobian is not constant in time, and you actually learn some interesting features over which you're going to make predictions. Okay, so this model is interesting and it doesn't capture some of the important things that happen. Okay, so of course people understood this essentially right away. And the point is that there are several things you can do to modify the setup we have to actually study feature learning. Okay, so let me just list a couple of the options, and the rest of the lecture I'm going to focus on one of the options. That's a finite width corrections here in a sense. Okay, so to study realistic networks. Okay, by realistic, I mean ones that are capable of actually doing feature learning. There are essentially 4 options. Okay, so option number 1, and this is what we're going to do. We're going to consider all the hidden layer widths to be large, so proportional to some number n, but finite. Okay, so we're going to consider wide networks and compute 1 over n corrections. And we'll see that in these 1 over n corrections is a lot of information. Okay, that's what I mean by finite width corrections. So finite networks are capable of learning features, fine. But there's a bunch of other things. You could take large step sizes. Large step sizes. I've said this a couple times, but it's important. So here, what I showed you last time is really gradient flow, just infinitesimal step sizes for gradient descent. But everything I said works for sufficiently small step sizes in gradient descent. But in fact, in practice, you find often choosing large step sizes gives you better results with your neural network. And indeed, when you choose large step sizes, you're no longer going to be in this linear regime. Okay, so that is one thing people study. It's quite an interesting question, how to do that analysis and what really happens. So another important thing is that, you see, when we did this kind of training, we fixed the number of data points. So maybe I was too sneaky and I didn't tell you about that. But here, really, you fix not only the depth and the input and output dimension, but you fix the number of training data points. And you study the situation where the model becomes more and more complex. But you could take the number of training data points to infinity with the hidden layer weights. Okay, so you know that this is an important thing to do, even just from just classical statistics. Okay, if you just have a linear model, forget about a neural network, and you make, usually they call this n observations. Okay, there's a class of notation, that's the number of samples you have, and you're in a p-dimensional feature space. Okay, you have p parameters that you're using to fit the data. The whole point is that you're supposed to scale n and p together. That's like what the Marchenko-Pasteur theory is about. That's what like basically half of high-dimensional statistics is all about. So you have to increase the size of your training data set together with the size of the model to get interesting answers. And that's what people do in practice. The more data you have, the larger neural network you use. Okay, so this is like non-parametric statistics, if you want to say it that way. Okay, and the final thing you can do, and people do this, and it's really interesting, is you can change the initialization. You can take what's called mean field initialization. Okay, so nobody said that this was the only way to choose the initialization scheme that you have. And okay, this is a good way to do it, but there's a subtle but very important difference that you can make. You take the exact same initialization scheme that I propose here, except that in the last layer, you make your output weights significantly smaller than they were before. Okay, that's for various reasons called mean field initialization. And what happens is, in the infinite width limit, neural networks are not linear models. And for example, one-layer networks and their optimization turns into optimal transport. Okay, there's beautiful connections to things people know, and you get like gradient flows on like spaces of probability measures more generally. You get sort of collective, interesting PDE that describe the evolution of these things. It's kind of a beautiful story, and we're not talking about that either. Okay, so there's other things you could say, but basically, like my plan today is I just want to do this one. That's kind of where I've got. Okay, so let me just stop. That's like the end of the introduction. Okay, so I want to like ask if there are questions or comments about it.
Can you repeat just one more time what is exactly mean field initialization in terms of the variance of the W?
Yeah, so what you do is you take the W's in the final layer only, and you take them, instead of being, let's say, roughly like this, that's what I wrote over there. You do something, and you just put a square here. Cool. Pretty much the game. And so what happens is, as a result, your network gets initialized to 0. But the gradients do not get initialized to 0. So you get an interesting set of deterministic, basically, PDEs that describe the evolution of the network. Sometimes deterministic, sometimes not, actually, depending on how you set it up.
Is this somewhat related to large step sizes, in the sense that the fact that the gradient tends to be bigger, it's a sort of stochastic version of large step size?
It's related to the fact that in the final layer, you have significantly fewer parameters than in the previous layers. You know, if you think of the previous layers as big, if the width is n, you have n squared parameters. But typically, your output dimension is just finite, 10, 100, 1,000, whatever, but you only have n parameters. So somehow this asymmetry ultimately causes you, at one point of view, causes you to be in what I call the anti-K regime. This is like the. So yeah, there's lots of ways to slice it. Those questions or comments?
Just a general question about the really percentage. So you always consider random fully connected networks, but do you think it works when we apply for convolutional neural networks?
Yeah, so it's a great question. I should have said this, and I kind of didn't, I think. So what I tried to emphasize partly last time is that you only need 2 properties of these networks to really do the analysis I'm presenting. One is that these networks are a Markov chain with respect to the layer index. That's true for every network you'll ever define. That networks are compositional, and that's what gives them the Markovian structure. So fine. And the second is you have to be able to analyze the one-step transition probability. Okay, but you can easily do that for convolutional networks. You just have to go to the Fourier domain. You can easily do that for residual networks. It's just you have a slightly different propagation equation. So you can do this for almost any architecture under the sun, okay, with some exceptions. You can't do things like batch normalization in general. That's very hard. It's a non-local operation. It's significantly harder to do this for attention networks or transformer type networks. There's things people do in practice that are harder to study. But I view that as a good thing. That gives you something to do late at night when no one's looking. Right? That's good. Other questions?
Maybe I have a easy question. So to study realistic networks, you mean that we want to do some feature learning, moving from the almost linear domain to somewhat finite.
Precisely. Yes. Yeah, so for me, like in this sense, I think a little bit like a physicist. Like there's some phenomenology, and you'd like to ask, what's the simplest toy model that really correctly allows you to reproduce it and make good predictions? And I'm saying this is a toy model, but it's too toy. It allows you to understand some things. How do you choose the weight and bias variances? What are some aspects of the effective depth? But it loses too much information. So you got to do something to make your life harder. Okay, good. So what's the main message that I'm going to try to give you today? Okay, so this was the introduction to like the setup, and now let me tell you what, in some sense, the answer is. Message. And then so my plan is like this. I want to roughly state what happens. Okay, so now I'm only going to consider this regime from now on. I'm going to consider the same kind of neural networks. In fact, I'll only consider them at initialization. And I want to explain what the structure is of the 1 over n corrections and how you think about them. Here's the main message is like this. Okay, so after choosing CB and CW, I put in quotes correctly. Again, I'll explain this at their time. Namely, you see you have this recursion that relates the 2-point function, the covariance at layer L plus 1 to the 2-point function at layer L. And it depends on CB and CW and sigma. And choosing them appropriately is to ensure that this recursion doesn't explode or decay exponentially in L. Okay, that's some kind of fine-tuning property. So correctly, good. The field ZL plus 1 is determined, or okay, the law of the field is determined by the following thing. So it's something that I think of as the effective depth of the network. Effective depth. I wrote this at the very first lecture, but I want to remind you. Okay, so by definition, the effective depth is going to be the sum of the reciprocals of the hidden layer widths, which you should just think of as being the ratio of the depth to the width. Okay, for me, all the hidden layer widths are roughly the same, proportional to confidence. Okay, so I'm going to try to explain to you on a number of things that really how nonlinear you are, how deep you are, how interesting you are, how far you are, okay, whatever, from the linear regime is controlled not by L. You typically think about larger L giving you more complicated networks, but it turns out that it's actually L over n. Okay, so let me say some words about it, then I'm going to try to convince you that L over n is a reasonable thing, and then I'll try to prove a theorem. Okay, so little by little. Okay, so this thing, so in fact, so L over n controls the following things. So all the following things are determined essentially by this ratio. So how close are you to the Gaussian process limit? So distance to a Gaussian process. So we were discussing this with Domenico in various senses. Okay, I'm going to state a theorem for you, which in some way makes precise the fact that if you ask, how close are you to being a Gaussian process? How close is this theorem to being true when the n's are large but finite? Okay, well, it gets closer and closer to true as n grows, but it gets farther and farther from true as L grows. And so you see, you'll never understand that aspect of the effective depth without studying depth over width. Okay, so that's one thing that happens. So the correlations between neurons, correlations between different components. So I study ZL plus 1, let's say 1 of X, and ZL plus 1, 2 of X. Right, so what happens in the infinite width limit is every neuron is independent of every other neuron. It's pretty sad, right? In particular, for example, the outputs are independent of each other. The IIT draws of the same Gaussian process. But like the whole point is to learn correlated things, right? It's not great. And so it turns out if you ask at finite width, how correlated are like these random variables, let's say for the same x or for different x's, it doesn't matter. It's also controlled by L over n, so I'll show you that. Okay, so then there's other things like the extent of feature learning. Extent of feature learning. Okay, so i.e. the change in what yesterday I called the NTK, capital beta, or if you want, just the change in the gradient of network from initialization. So again, like, right, this theorem was basically saying your gradient never changes. You can just keep the linearization at the start of training. It stays the same forever. And I'm saying at finite width, how much does it change? Well, it turns out it changes like L over N. Okay, and so on and so forth. Dot, dot, dot. Okay, I ran out of room, but also there's no point in writing everything. I'm saying that roughly speaking, you should think of L over N as like a good summary parameter for at least a lot of things at the start of training. Much better than L separately or N separately. Okay, so I'm going to do some erasing and try to do something concrete. But are there comments or questions about this? That's kind of the point I'm trying to make today at a high level. I know it's not precise yet, but I promise it'll be very precise. I'm going to erase and see if there are questions in a moment. So let me keep this. So here's basically my plan. My plan is I want to explain to you a little bit how to think about why it's L over N rather than something else. And also in the course of doing that, to show you what I've already shown some people, is my favorite computation about neural networks. Okay. It's a little strange to have a favorite computation, but it feels strange to be a mathematician, so it all works out. Are there comments or questions about that? All right, good. So what I want to say is I want to say why L over N. How would you guess this? Oh, okay. So let me make 2 points essentially. So point number 1 is like this. First, let me explain why you should think of L and N as pushing in different directions.
Not the net.
Maybe, hopefully not. Okay, so I want to just advocate. You know, I drew this kind of picture at the beginning, but again, I want to say a little bit more precisely now, maybe. In fact, I can't exactly remember the picture I drew at the beginning, so I'm going to draw it again potentially. Right. So first, I'll explain why it's the ratio, but in general, for a general neural network, how should you think of this? Okay, you can think like a person who does dynamical systems. You can think of L as being a time parameter. Okay, it's like saying you're watching a dynamical system evolve, and your time one dynamics is you apply a random affine transformation, you apply your nonlinearity. That's like one layer is time. And N, therefore, in this analogy is like the system size, the number of degrees of freedom. That is literally like how big is your state space at each layer. Okay, I'm thinking of them as all the same for this analogy. Okay, and like already from this point of view, this should kind of convince you that L and N fight each other, right? Bigger systems take longer to come to equilibrium. And so it's like the bigger N is, the longer I should wait for L to be larger and larger until I get some kind of ergodic behavior. Okay, so that's like the very general point of view. But let me make this very precise, like extremely precise. So let me consider a special case, which I love for a variety of reasons. So I'm going to consider what are called deep linear networks. Okay, so sigma of t is just the identity. Good. If there are no sigmas, you take the sigma out of the game. Okay, you set the bias variance to 0. You set the weight variance to 1. Okay, so what do you get as a result? Well, you simply get that the output of your network. Okay, we'll set all the NLs equal to each other, just like I've done in the picture. Okay, the output of your network is simply a product of Gaussian random matrices times the input. That's all it is. Okay, so now you might say, who cares about this when you care about nonlinear networks? Well, it turns out that actually even these linear networks, although, okay, they're called linear because, of course, they're linear in X, they're still very nonlinear in the W's. And understanding various things about optimization about them is quite interesting and actually complicated. even in this setting. But for our purposes, I want to just explain for these matrix products what is going on. Okay, so like these matrix products have been studied a lot, and they're studied typically in two regimes. And you should tell me if I already said this. I can't remember if I said this in the first lecture. Did I say all these things?
Yeah.
Yes, people.
We remember the picture.
Okay, but I didn't do the calculation.
No.
No, okay, excellent. So let me say the words again. The words are always nice. Everyone likes
Yeah.
words. Okay, so this is like the free probability regime, right? That's how a mathematician would think about it. You take a product of finitely many random matrices. It's a maximum entropy regime. Okay, L equals 1, for example, or L equals 0 in my notation. This is like Wigner's random matrix theory or Bischart's random matrix theory, whatever. But now we have more words we can associate to this. This is like the Gaussian process or the neural tangent kernel regime. Okay, this is the regime where you fix the depth, you let the width go to infinity, the network's kind of trivialized. Very nice. Okay, there is also this regime, multiplicative ergodic theorem regime. This is the study of long-time dynamical systems, wrapping up exponents and so on. I'm sure I said all those words. Okay, and here, like I said, oh, now it's coming back to me. You're right. I said untrainable. That's what we'll see in a sense. And I want to explain on this picture that basically this limit where you fix L and you let n go to infinity just very much doesn't commute with the limit where you fix n and let L go to infinity. And I want to show you that really it's the ratio of the two of them that controls what's going on. And I want to show it to you on the simplest possible random variable you can construct from this network. Okay, you fix an x. Let me take x to have norm 1, so I can make my life easy. And you just study what is the size of the output that you get. Okay, it doesn't get any simpler than that. And I claim that already this thing tells you a lot about what's going on, and in particular explains why L over n appears. Okay, good. So now, question for the students in the audience. Okay, ready? So let's fix L, and let's send n to infinity. Okay, so what is this going to converge to? I claim that this norm has an almost sure limit. I'll have any students in the audience. People who are students at heart can answer as well. What are you going to get? So remember, these are like big Gaussian matrices, right? And the WL IJs are all Gaussian, mean zero variance 1 over n. So each of them looks like the standard kind of Gaussian matrix one typically considers. Anyone know? Okay, so it's not too bad. You just have to recall a fact. So the fact is, when you normalize your matrices like this, these matrices are very, very close to being isometries. They're very close to preserving lengths and angles. Okay, so in particular, if L is fixed, then since each of these matrices is very close to preserving lengths and angles, the whole product is going to be close to preserving lengths and angles. And therefore, you're just going to have that the length of the resulting vector is just the length of the original vector, which was 1. Okay, very nice. So you get 1 almost surely. Okay, good. Now, more interesting, what happens over here? Okay, you fix n, you let L go to. I'll do this derivation for you in just a moment. It just takes 1 or 2 lines. But it's more fun to guess the answers first, because that's my usual strategy.
For me, it's 0, but I don't like
Well, okay, your intuition, your pattern matching is excellent.
It becomes determined. The matrix, at least the dimension of the number of matrix that you multiply.
That's right. They become bigger and bigger, correct? So, but why is it 0 and not infinity? I feel like the only 2 possible answers are 0.
Ah, yes, okay.
Right? I mean, like somehow I already have 1, and there's supposed to be like an answer.
Yeah.
Okay, so but you're totally right. Okay.
The other way around.
Okay, so the reason it's 0, this is like something that's maybe slightly harder to guess, is that typically what happens is when you study a product of L matrices, let me just go down to L for a second. If you want to keep their singular values bounded, what you do is you have to raise it to the 1 over L power. That's the usual normalization. It makes sense. Take a product of L things, you want to raise them to the 1 over L power so that things stay reasonable. And indeed, the theorem is that the singular values of this kind of product of matrices raised to the 1 over L power converges to something in 0, 1. Okay, they're a little bit less than 1, but that's with the 1 over Lth power. So when you raise it to the Lth power, you're taking some numbers less than 1 and you raise them to higher and higher power. They all go to 0. Okay, so that's why you get 0 instead of 1. Okay, so you see that just on the level of this really simple observable, you need something interesting for like your phase diagram, so to speak, to like explain how to interpolate between these two regimes. Okay, so now let me explain why it's L over N rather than something else. Okay, so I'm going to, maybe amazingly, I claim it's easy to write down the exact distribution of this random variable non-asymptotically. It's a beautiful thing. So here we go. I give this problem to my students because, well, it's easy when you tell someone how to do it. You know, it's just hard to imagine that it might be possible. Okay, so what's the difficulty? Well, the difficulty is that the norm of the product is not the product of the norms, except it is. Okay, we're about to see. Okay, so it's not, but it is. Okay, so the first step is like this. Okay, what you do is you just multiply and divide by the norm of the first term. Okay, so far that was a legitimate move. Okay. Okay, now what's the point? The point is that the matrices W are IID Gaussian, right? So this thing here is a uniform unit vector on the sphere. And in particular, it's independent of the norm of the Gaussian vector you get, right? W1 times any unit vector is just a standard Gaussian vector. This norm is independent of its direction. Okay, moreover, the distribution of the norm is what? It's just the square root of the sum of the squares of a bunch of independent Gaussians. It's just a chi-squared random variable with n degrees of freedom, okay, normalized by the variance, which is 1 over n raised to the 1/2 power, right? Like this thing is the sum of the squares of n standard Gaussians, but I have variance 1 over n, and I took the square root to get the norm. So I know the exact distribution of this thing. Okay, now obviously I just repeat. Now again, this is some unit vector. I multiply by a Gaussian matrix, and I keep going. And what do I get in the end? I get exactly that this is equal in distribution. Okay, the product on L goes from 1 up to capital L plus 1 of a bunch of chi-squared random variables with n degrees of freedom raised to the 1/2 power. So it's an exact formula that's valid in distribution, non-asymptotically. It's a beautiful thing. Okay, so that's what I mean by the norms kind of are like the products. It's like it's a beautiful property of Gaussians, basically. Okay, so before I write anything else, let me already point out, you see the fight between L and N starting. Okay, each of these random variables concentrates really quickly around its mean, which is 1. Right, but it's got a little fluctuation. So somehow making n bigger causes the norms to be distorted less and less and less. That makes sense? That's what we guessed up here. However, you know, because I'm taking the product of L such things, making L bigger is going to cause the fluctuations to be more and more and more important. Right, so there's going to be a fight between them. And to make the fight easier to understand, let's write it as x sum log. Right, x sum and L goes from 1 up to L plus 1, 1/2 the log of a chi-squared random variable, n degrees of freedom appropriately normalized. Right, that's okay. So you take a product of IID things and you write it as the exponential of the sum of IID things. Right, that's good. Okay, but now what's the point? The point is the thing in the exponent is a sum of IID things. So nothing can stop you from understanding it. So in particular, what do you find? So you find that when L is bigger, is like becoming large, you can just apply the central limit theorem to these objects, right? These are all IID random variables. It's easy to compute their mean and variance. And what do you ultimately find? You find an exponential with a Gaussian. Okay, so the mean turns out to be minus L over 4n, and the variance turns out to be L over 4n. Okay, the mean of each one of these has order 1 over n, and the variance of each one of these also has order 1 over n, but you add up L of them. That's how it looks like to leading order. And so now you see L over n emerging. You see the effective behavior depends only on the ratio of L and n, okay, with some universal constants thrown in. Again, and here's what you find basically. Okay, you can interpolate between these two regimes now very nicely. Okay, you introduce L over n as a constant. Here L over n equals 0. Here L over n equals infinity. And here you get, okay, up top, you get a Gaussian with mean 0, variance 0, in other words, 1. Okay, that's good. That matches what we got. Right? And over here, you get a Gaussian with mean minus infinity, standard deviation, square root of infinity. So you get e to the minus infinity, in other words, 0. Because you get a nice smooth interpolation once you add this kind of parameter. Right? So it's the picture is you would normally draw it like this square, but things are not smooth here, so you blow up the corner of the square and you introduce a variable that parameterizes how you approach the corner. Okay, so again, you see the effect of L over N, and you see each layer gives you a 1 over N correction, but you add them up. And so eventually you get an L over N correction. That's the basic mechanism by which the importance of depth is only seen at finite width. The point is this kind of picture is actually true for completely general nonlinear networks as well, and for the same philosophical reasons. It's just not so easy to derive. But I'm going to derive a part of it today. Okay, well, I'll do as much as I can. Okay, so let me pause. This is like my attempt to explain what L over N is trying to do for us.
When you say non-linear network, you say sigma, not identity.
Yeah, exactly. I'm just saying take the right sigma, and then as I slightly vaguely gestured, here I just told you what to do with CB and CW. There'll be a slightly different thing that you do. And then I'm saying you're going to get the same kind of answer. How close you are to being up here is going to be measured by the ratio of L and N. So if it goes to 0, you'll still be close to a Gaussian process. You'll still be close to the NTK, whatever. But as L over N grows, the kind of thing you'll find is that you are farther from the linear regime, but you're numerically less stable. So you want to be a little bit into this regime, but you don't want to be too far into this regime. At that point, everything has infinite fluctuations. You can't do it on a continuous. There's things called exploding vanishing gradient problems. Okay, whatever. There's some names for these problems. Yeah. Other comments or questions?
The chi-square at the different layers are still basically independent.
Yeah, that's the point. They're still like for Gaussian weights with the linear thing, they're just exactly. If they weren't independent, I wouldn't have won much. I mean, because in general, I would have to somehow deal with that. And for a neural network with nonlinear activation, they're not really quite independent. But they're close, and okay, you can try and say something. Other questions or comments? Okay, very good, very good. Okay, so here's basically my plan now. Let me do this. So I want to make a definition or two. Maybe I'll erase this as well. So I'm going to make a definition. I'm going to remind you what cumulants are. I'm sorry, many of you probably know cumulants better than I do. But nonetheless, I'll remind you what a cumulant is or what a connected correlation function is. And then I'm going to state the theorem that I'd like to prove in the second half of the lecture, or at least to basically explain how the proof goes. And it will be all about how do you compute finite width corrections. Okay, so before I start, maybe I think it's reasonable to say that, like, okay, when you have something whose limit is Gaussian, and you're trying to study something that's almost Gaussian, like, how do you do it? Like, what's the mathematical packaging that you will try to use to say that something is close to Gaussian? Well, like, a natural way of doing it is to study the cumulants of the resulting object. I'll remind you, but basically Gaussians are distinguished by the fact that only their first two cumulants are non-zero and all the other cumulants vanish. And so you can study how close to zero are the other cumulants. Okay, that's the basic thing you do. Okay, so fine, so good. So now let me move to general sigma and remind you a little bit what's happening. Okay, so here's definition. Definition. Maybe I'll say recall this way. So recall that if x is a random variable, so it's just a real valued random variable, then we make the following definition for the cumulants. Okay, so here's a classic thing you can do. You can take the expectation of e to the tx, okay, the moment generating function of x. Laplace transform, okay, you can call it whatever you want. And okay, so like, great. And now what you do is you view this as a power series in t, and you take the logarithm of it. It seems like a random operation if you've never seen it, but You can just do it. No one can stop you from doing this. And you can define the resulting power series in T like this. Okay, so the resulting power series in T looks like T to the K over K factorial. And then there are some numbers, which I'll call kappa K x. Okay, and these numbers are called the cumulants of x. That's the definition of cumulant. They're the numbers that appear in this expansion. Okay, so that's a horribly like short definition.
Why not take a basic function?
You just put an I in front of the T. You just treat everything as a formal power series. So I just forget where the I goes with the plus or minus. So I think I prefer to do it this way, but I mean, yeah, you're totally right. Okay, so like, look like some remarks, again, to like orient ourselves, so to speak. Okay, so in general, kappa 1 of a random variable is its mean. And kappa 2 of a random variable is its variance. Okay, so it's cool. Rather than studying the moments, you automatically, in a sense, get the right normalization. You see, instead of studying the second moment, you get the second moment minus the square of the first moment. It's kind of like automatically doing some subtraction. Okay, if you've ever done generating functions in combinatorics, logarithms are beautiful, magical objects. Okay, so that's point number one, that you know these things. And in general, they're always polynomials in the moments of x. That's kind of obvious. What's less obvious? Okay, let me not say it. Fine. I'm not going to say it. Okay, so that's point number one. Point number two is that if x is Gaussian, right, mean zero variance, let's say sigma squared, then what? Well, the log of the Laplace transform of x. Okay, so in this case, we know exactly how to compute the Laplace transform, right? It's just like 1/2 of like t squared with the sigma squared or something like that with an e. So the e kills the log. I just get, okay, so let me put a mu. Can't help myself. Okay, so I get something like t mu plus t squared over 2 sigma squared. Okay, so this is again saying, like for Gaussian, all the other cumulants are 0. Okay, so it's just a nice characterization of a Gaussian. You're Gaussian if and only if this is true, because you're Gaussian if and only if your Laplace transform is the right Laplace transform, if you want to say it this way. Okay, beautiful. And so in general, what we're going to do is we're going to say, okay, x is going to be the distribution of one of these neurons, which is not going to quite be Gaussian, it's going to be close to Gaussian. And we're going to try to understand how the cumulants actually behave. They're all going to go to 0. Like when you write this out, in general, you'll have plus ... but all of this stuff is going to go to 0 as the width goes to infinity, and we'll be interested in understanding it. Okay, very good. So that's my 2 remarks. And now let me tell you what kind of cumulant I wanted to study. So let me see what kind of notation I had. Right. So let me make a definition. So a definition. So let me say kappa L4 of x. Okay, so sorry, I'm back in neural network land. That was like a short digression into just like a definition, just so we're all on the same page. Okay, so I fix an input to the network. That's the x. L is the layer index, and 4 is going to be the 4th cumulant. Okay, so for me, by definition, it's going to be 1/3 of the 4th cumulant of what happens when you, for example, take the value of the first neuron in the out layer evaluated in x, that random variable. Okay, that's a scalar valued random variable, so you can apply the definition above. Okay, and there are multilinear generalizations of these definitions, but it doesn't matter. Okay, so this is the object I'll want to study. You see, this 4th cumulant necessarily goes to 0 in the infinite width limit because the distribution of this random variable is Gaussian. But it won't be 0 in the finite width corrections world, and so we're going to try to understand it. Okay, and so okay, this is great. So I want to give 2 interpretations for what this cumulant is trying to measure. Actually, maybe 3 interpretations. Okay, before I state a theorem about it. So we can think of like this thing intuitively, kappa L or of x, in 3 ways. Okay, so the first thing is kappa L of x measures the distance to Gaussian. A measure of a distance to how close you are. How close it is to 0 tells you how close you are to Gaussian. Okay, it's a very incomplete story, but still, that's like the basic intuition. Okay, the second thing is you can just write out a formula for kappa L4 of x. Okay, just like you can write down a formula for these kappas, I'll spare you the details. Okay, for centered random variables, you have the following expression. So it's equal to 1/3, just because I have the prefactor of 1/3. And then, okay, in here, I have to calculate something. So what is it? It turns out to be the fourth moment, okay, of CL1 of x minus 3 times the second moment squared. Okay, CL1 of x squared, close bracket. Okay, like this is the thing that goes to the 0 when you're a Gaussian. Right? This is like how you compute the fourth moment of a Gaussian. It's 3 times the variance squared. Okay, but the reason this formula is good is you see the fourth cumulant, kappa 4, captures something about the variance of ZL1 of x squared. It captures something about fluctuations.
Or this is true in general for any random.
This is true for any random variable, correct? Well, any centered random variable. Or sorry, yeah, centered is actually not for this. I don't need symmetry. Okay, so i.e., like you could say the variance of CL1 of x squared, that's like going to be my basic object I want to think about. Okay, I have to think about this. So this is like, oh God. Oh God. Okay, I'm going to mess this up. One moment. Okay, this minus this. Okay, good. 3 times kappa L4 of x plus twice the expectation of CL1 of x squared. I think I got that right. Okay, so it's like if you believe that the way you've initialized your network is that the expectation of the square is like order 1, then the only thing that could cause you to grow is kappa 4. Okay, so it measures like the fluctuations of your random variable that you're studying, which is like the value at the nerve. Okay, so anomalous fluctuations are captured by kappa 4. That's interpretation number 2. And interpretation number 3, this one's less obvious, but I'll leave it to you as a fun exercise. Okay, there's another formula which I really like for kappa L4 of x. It's actually the covariance between CL1 of x squared and CL2 of x squared. Okay, so it captures the correlations between neurons. Okay, like in the infinite width limit, these two random variables are literally speaking independent of each other. The covariance is obviously 0. But okay, it's not completely obvious. That's not how I defined it, but it's basically by symmetry. Like all these things are like sourced from the previous layer in a symmetric way. Yeah, I'll leave it to you to do the calculation. Although secretly we'll do this calculation in the course of the proof. Okay, so you get like, if you want, you get fluctuations. I think of this as fluctuations. And I think of this as like interneuron correlations. So that's like maybe some more reasons to study kappa 4.
It's the correlation, sorry, it's the correlation between the square of the neuron.
So you see, all the neurons are symmetric around 0. So if I didn't have the squares, it would just be 0 bad reason. Like you might conclude that maybe they're independent, but they're not. So I fix it by taking the square, and then I study. Okay, perfect. Okay, we're doing well. Ready almost to state the theorem. Okay, that's it. Are there questions or comments about this?
Measures distance to get Gaussianity. You are telling us that it's not.
Well, I'm just saying.
To understand like.
No, you should understand from this calculation. Gaussian, if and only if all the higher cumulants are 0.
Right, but why?
So
the third of the.
So true. So okay. All the odd cumulants for our thing will be 0 because they're symmetric around 0. But it turns out that as I'll state in the following theorem, in fact, this is the first order correction in 1 over n. All the other cumulants are actually lower orders. That's like.
Can you repeat once again why we have this factor 1/3 inside of the?
Well, cumulants have to do with like factorials. And like basically, when you write the Z1 4 times, right? There are three ways to choose two pairings among the C's, like pair partition of the C's, and the 1/3 is natural. And I think of the kappa, the 1/3 C goes away when you do this. So it's just a convenience thing. The formulas turn out something nicer. It doesn't matter. It doesn't matter. But like this is how it appears. But I'm gonna say.
So if you were to normalize higher order cumulants, it would be just the number of pairs that you can take out for the 6th order cumulant. It would be the factor would be 15 or something like that.
Yeah, it's like 1/6 choose 2 choose like 2, 2, 2. Yeah. You know, like that, like all those.
They are normalizing like for the higher order moments of the.
That's right. That's right. That's you can think of it exactly that way. Yeah.
The dot line to the right.
Yeah.
This is the moment of order 2, not the variance of the square of Z1, right?
No, the variance of the square of Z1.
Okay.
You just read it from this. You see, this is the square of the square, but here I have 3 times the square of the square squared. So one of them is the variance and the other one has a 2. And take the 3 and I multiply. Okay, so I think I got it right, but I'm really bad about these things, so you should like correct me. Great. Okay, so just enough time. So let me now state the theorem that I want to prove. And let me be a little strategic. I think maybe I'm going to try to state the theorem over here. Okay, that way, like I can try to prove it on the right. Very good. So there's what I'd like to prove. All right. So I wanted to leave this up because it's important conceptually, I think, to compare. What was the infinite width theorem telling us? Everything is Gaussian. It only depends on 2 cumulants. And moreover, there's a recursion that relates the second cumulant at layer L plus 1 in terms of the second cumulant at layer L. You think of it that way. Okay, same thing is true for all the cumulants, it turns out. Okay, so we have following recursion. Okay, so kappa L plus 1 for of x. So the fourth cumulant at layer L plus 1 can be written like this. Okay, so there's a constant CW squared over n L plus 1 times the variance with respect to the infinite width Gaussian that you have of C squared at C1, oops, CL1 of x. Okay, so this is a constant which you already know if you've already solved the infinite width kernel recursion, and it has a 1/n prefactor in front of it. Okay, plus there's another constant, okay, it's CW over 2 times the expectation with respect to the infinite width Gaussian of the second derivative of sigma squared at C1 of x, and this constant squared times kappa L4 of x. Okay, so there's a recursion which relates the 4th order cumulant at layer L plus 1 to the 2nd order cumulant at infinite width, just the covariance at the previous layer, and the 4th order cumulant at the previous layer. It's like the start of an upper triangular system if you want. This is like the world of integrable hierarchies or something. Okay, plus errors in order n to the minus 2. Okay, so again, I'm now in the setting where my hidden layer widths are all proportional to n. That's my large parameter. And you see that this recursion immediately tells you that in n, this cumulant is order 1/n, right? Because the recursion for it is basically like this. It's a constant over something of order 1/n plus a constant times the previous thing. Okay, so very good. Okay, so but wait, there's more. Okay, so let me draw this in a different color. And then, okay, so this coefficient here has a beautiful interpretation. It actually turns out to be like this. It turns out to be the derivative of the variance at L plus 1 layers by the variance at L layers squared. Okay, so it's telling you how much is your infinite width kernel changing from layer to layer. That's an equality, which is not obvious at all. Okay, so if this is equal to 1, which is what tuning to criticality is basically about, it basically asks, that your kernel doesn't change exponentially by a multiplicative constant from layer to layer. Okay, part of tuning to criticality asks that the derivative of the kernel at layer L plus 1 with respect to the kernel at layer L be very close to 1. Okay, so in fact, the constant in this recursion looks like this. So if you set that constant equal to 1, what do you find? You basically find that KL plus 1 for of x is some constant, okay, which divided by n, plus something that looks like 1 times kappa L for of x. That's kind of the form of the recursion you find for an appropriate constant. And what do you see? It's very easy to solve a recursion like this. Okay, what's the dependence on L of kappa L for of x now? Okay, Domenico knows, but he's too polite to say. If you have a recursion of the form constant over n plus the previous thing, what happens when I iterate this recursion? How does it grow with L? Linearly, okay, very good, right? You get this constant at the same layer, at every layer. So this implies, indeed, the kappa L plus 1 for of x actually looks like L over n plus lower order correction. Let me drop the lower order correction. That's what it looks like. So you see, again, it's the picture that I drew before, but in a different way. You might have thought that kappa L4 becomes less and less important because it has order 1 over n. Okay, so as the width grows, it becomes closer and closer to 0. But in fact, as the depth grows, it becomes larger and larger. And they fight each other precisely so that your distance to Gaussian, it just doesn't go to 0. Like in particular, the fourth cumulant doesn't go to 0 if L over n remains constant. They bounded away from 0. And this kind of thing generalizes to other cumulants. Very good. Okay, so let me write one more thing because we're going to need this for the proof, moreover. But also because it's fun. I think it's fun. Okay, so oh my God, where is it? So let me define GL of x. I'm going to call it just GL. So L is a fixed, x is a fixed input. It's just going to be the finite width version of KL. Yeah, I think I called this, maybe, I should not remember what I called this. It doesn't matter. Okay, so this is just saying you grab any neuron you want in layer L. My input x is always fixed in this theorem. And I just ask, what's the expectation of the square? In other words, the variance of this thing. Okay, so when n goes to infinity, GL converges to the infinite width value of KL. But in general, at finite width, it's just not quite the same. Okay, it's a little subtle. Just think of GL equals KL to leading order. Not that, but still, I want to be precise. So moreover with this, here's what we have. Here's another thing you can do. So suppose you want to compute the expectation of some function, any basically function f, evaluated at some input, okay, and some collection of neurons. So one way of saying how close are you to Gaussian, okay, when n is large, is to ask how close is this to being a collection of independent Gaussians. Right, and so I'm going to write down the start of a perturbative expansion in powers of 1 over n for these expectations. Okay, so here's what you get. The first term, let me write you. Okay, the first term is just the expectation with respect to GL of f. Okay, let me explain this. So when I write this, I just mean you treat each of these as independent mean zero Gaussian, but just with this variance. Just like I wrote before, right? The expectation with respect to KL means each of the ZLI of X alphas are independent with respect to the I variable. Here I took I equals 1, and they're mean zero Gaussian with this variance. Okay, that's my, so this is just a Gaussian integral. Very good. Plus, okay, here comes the fun part. You get KL4 of X over 8. Okay, yes, you do get 8. The 8 is important somehow. Times the expectation with respect to the infinite width variance KL of the following operator. So you take the sum on J goes from 1 up to M. Maybe I called it I goes from 1 up to M. You take the second derivative with respect to ZI, ZI of X squared applied to F. And you again compute a Gaussian integral. The point is that you are basically expanding the expectation of F at finite width in terms only of Gaussian integrals in which the neurons are mean zero and independent. and you get this term. Now you know this is a 1 over n term because kappa L4 of x has order 1 over n. And your corrections to this expansion, if you can in principle expand any one you like, are order 1 over n squared. Okay, so like this gives you these two things basically turn out to be completely equivalent actually. But it's like if you like the word of like local operators, right? You're trying to compute the expectation of an observable f. And when you do perturbation theory, you have to insert a local operator, which is some derivatives at the points where you evaluate f. And then you compute back in the theory you're perturbing around. You can say it in like whatever words you like. Okay, so let me stop. Let's take a 5-minute break. Already 5 minutes over. But let's come back at like 11:10. And I will try to sketch how a proof of this kind of theorem works to illustrate, you know, how one understands finite width corrections. Okay, I'm happy to stick around. I'll take people's questions in the break too. Okay, so let me try to explain the proof. I'm just going to give a proof sketch. I'm going to try my best to explain the philosophy and why it's really the same proof as what I gave you for the infinite width limit, except like, you know, you have to like, but the point is that it's really exactly what you think it should be once you think for long enough, but maybe everything's that way. Okay, so here's my proof sketch. Okay, so first of all, the most important thing is not to expand everything out and write all the things. Okay, you just got to stay calm. So I tell myself because sometimes I get too excited. Okay, so here's the first point. Okay, this is what I was saying about the Markov chain thing. Okay, so recall that given the vector of activations in layer L. Okay, so the vector of activations in the next layer is very simple, right? Every coordinate was just independent Gaussian. The one-step transitions for these things are very trivial. Okay, so what do we get? We get the following thing. Oh my God. Right? So we get the components in the next layer, the L plus 1 of x, are just IID Gaussian, mean 0, with a covariance that in the second lecture I defined as KL plus 1. Okay, I'm going to drop the of x. Everything's evaluated at x. Okay, our IID. And then we had a nice formula for k hat. Okay, k hat L plus 1 was equal to, okay, so you have CB plus CW over ML times the norm of the vector of sigma applied to ZL of x. Okay, that's a perfectly coherent statement. I condition on something, and I get a distribution which depends on the thing I conditioned on. All right, that was the starting observation that, hey, everything is Gaussian given the previous layer. And moreover, remember the covariance of the previous layer had this very special form. It had the form of an average of things at the previous layer. That was like this beautiful part. Okay, so now you right away see where GL comes in. Okay, so I'll write it this way. Okay, also, but I'm just going to rewrite this notation because eventually I'll delete the theorem. So GL, right, is precisely, if you think about it, the expectation of K hat L plus 1. L. Okay. Right, why? Well, because look, GL is the expectation of this square, right? But you just condition on the previous layer, and you get the expectation of the conditional expectation, in other words, the conditional variance. And then, okay, you just get that they're the same thing, right? Very good. So GL is the mean of the variance at layer L, but it's the finite width version of it. The infinite width version of this mean is the thing that in this infinite width theorem was K without the hat. Okay, so what does this suggest, right? What was the philosophy of the previous proof we had? The point is that these KLs were very close to their mean. That was the game, right? That was the whole proof of that. Once you know that the conditional covariance is very close to its mean, you just say, oh, cool, all the things in my layer L plus 1 are just Gaussian mean 0 with a deterministic covariance, done, therefore Gaussian. And so, okay, at finite width, they're just close to their mean, but you perturb. You do an expansion into difference. Okay, so we're going to write GL for the mean of this covariance or this variance matrix. And I'm going to write delta L for the difference from the mean. Okay, K hat L minus the expectation of K hat L. In other words, minus GL. Okay, so the philosophy of the previous proof is you can ignore delta. Okay, now delta is going to be the main star in the game. Okay, KL is our order parameter, and this is the fluctuation around the mean, and that's how you get estimates. Okay, so with this, the main estimate that I black boxed for you in the previous proof can be written like this, right? This now by construction is one of the things I was calling a collective observable that has mean 0 because I forced it to have mean 0. Okay, so in other words, the moments of delta L, how close is it to 0, the qth moment, look like this. They're O of n to the minus ceiling of q over 2. That's the thing I didn't prove for you, which is the hard part. Okay, so I'm saying this measures how close the finite width variance is to just a deterministic number, which is its mean. So here's going to be the game. I'm going to, in fact, start with this perturbative expansion for the expectation, and I'm going to explain how to repackage writing this kind of object only in terms of delta. Okay, and then once we know that the delta is small, anytime delta appears to a power, we can think of that as a power series in powers of 1 over n, right? Because the expectations of delta are powers of 1 over n. Okay, so here I go. So this is just like the preparation. Now you can just ignore all this if you want, and I'm going to start by explaining a little bit how to get this formula. Okay, so what do we have? Nice. We have the next page. That's what we have. Oh, yes. Okay, good. So, okay, we have. So I wanted to compute the expectation of some arbitrary function f. Okay, if you want to be very precise, it's some polynomially bounded function f, evaluated at a finite number of neurons. Okay, I will explain in a bit why having information about such expectations allows you to derive the recursion for the fourth cumulative. Okay, but let me start with this object. And I'm going to show you, so if you're a statistician, this is going to be something that's related to like the delta method or Edgeworth expansions or whatever their names for these things, but it doesn't matter. I'm just going to do it because it's easy in this context. Okay, so you know, the philosophy is the following. If something is Gaussian, you should always work in momentum space. Right? Working in position space is always a disaster because not only do you have to invert the matrix, but you have to compute a determinant. And okay, maybe you can do it, but I can't. So I'm going to work in momentum space. I'm going to do it. Okay, so this is going to be the integral of f hat of the dual variables c. Okay, so I'm going to have one dual variable for each random variable I have here. So this is going to be an integral over Rm. And then I have to write down the characteristic function of these guys. Remember, the characteristic function is what we studied to compute the convergence to the Gaussian process limit. Okay, so this is just x of minus I sum of okay, j goes from 1 up to m. I shouldn't have chosen I, but it's too late. Okay, cj z l j of x. Okay, the dc. I'm basically ignoring issues of convergence. I promise everything converges, but don't worry about it too much. Okay. Very good. Very good. So this is the starting point. And now my goal is to figure out how to relate this to objects at the previous layer, basically. And okay, you tell me, so to speak. All right. What am I supposed to do with this characteristic function? We already did it before. So for the people who are students following the class, okay, like how am I supposed to simplify this characteristic? Cool. Yeah, how do you do it? No, I don't want to do it. No, I don't want to do it. No, it's too hard. It's too hard, Domenica. You're too technical. No, can't do it. No. What's the structure of the neural network? There's only one property I ever use about the neural network. I happen to convenient. Everything is conditionally Gaussian, and cumulants are easy, and everything is easy for Gaussians, like the characteristic function. So let me first condition on the previous layer. Okay, compute the conditional characteristic function and then see where I end up. Okay, and this is already going to relate things to the previous layer. It's going to be a beautiful thing. Okay, so what do we got? We get this is the integral over Rm. Okay, you get f hat c. Now you get the expectation. So this expectation is over all of the things in layer L minus 1 and smaller. I'm just going to integrate out the weights in layer L. You get x of minus a half sum of I goes from 1 up to m. So we switch back to I. Okay. Doesn't matter, I'll put J goes from 1 to M, right? Conditional in the previous layer. Each one of these is an IID Gaussian, mean 0, variance K hat. So let me just put it in, right? You get CJ squared times K hat L. Oh, that wasn't too bad. That wasn't too bad. Okay, I made progress. Okay, why did I make progress? Well, first of all, okay, now I have something that looks Gaussian. I'm pretty happy about that. But second of all, you see, and this is like a key point, so I need to say this. So here I wrote KL plus 1, and KL plus 1 was something that only depended on layer L. So here K hat L only depends on layer L minus 1, right? That's the only thing that's important.
But this is too conditional on the previous layer.
I know, so in the expectation, that's why the outer expectation is still there. I write it as the expectation of the conditional expectation. I compute the conditional characteristic function, and I have to average it. That's the difficulty. And remember, in the infinite width Gaussian proof, we just said, okay, KL hat converges almost surely, or okay, converges actually just the probability we proved to its mean. So I can get rid of the outer expectation. That was the whole theorem, basically. But here, okay, I want 1 over n corrections. So what do you do when you want 1 over n corrections? Well, you add and subtract the mean. That's what we always do. That's what I always do. I don't know very many tricks, but I know that trick. And that's a good one. Okay, so what do? You get f out of c. So its mean, remember, is called g. I have a special name for the mean. So okay, so when you add and subtract, so the exponent is just linear in k. So this is like beautiful. Let me just write it this way. You just get the L2 norm of c squared, right? You just get the sum of the squared of the c's. Times you get GL. Times you get the expectation of x of minus a half c squared times delta L. C. That's what you get. That's what you get. Well, that's not too bad. Look, it's on like a third of a board. Okay, so what's the point? The point is that if this is gone, right? If you just say delta L is very small, I'm going to ignore this term. You just get the integral of f hat against the characteristic of a Gaussian, in which everything is IID mean 0 Gaussian with variance GL. Okay, that's kind of why the GL appeared in my expansion instead of the KL directly. But now what's the strategy? Well, it's exactly what I told you, right? Delta L is very small. So why not just expand the exponential and collect your terms? That's going to be your power series. Just going to do it. I just did it. Okay, well, I didn't quite do it yet. Okay, so now what am I going to do? I'm going to say, get f hat of c, you get x minus a half c squared times GL. And then I get the expectation of, okay, so even I can expand the Gaussian. Okay, now that I say that, of course, I'm going to mess it up, but okay, we're going to try. So what do I get? I get c squared with a minus over 2 to the q times 1 over q factorial, and then a delta L to the q dc. There are some convergence issues which I'm not dealing with, but they're actually all okay in this case because you have this Gaussian out in front. That is what they basically converge. So it makes this way easier than usual edge grip expansion. So, okay, now, the expectation. Yeah, pretty good. Look, that's the power series in 1 over n. That's basically the whole proof. That's why you can get all of the orders of 1 over n. But let me do it. Okay, when q equals 0, I get 1. Right? When q equals 1, what do I get? Okay, it's just following the notation. What do I get an expectation when q equals 1? 0. Okay, very good, right? That's good. That's how I chose delta L. That was the whole point of the method, right? Okay, and then the other thing you get is q equals 2. So I'm going to write that out. Integral f hat c nice x minus a half of c squared GL. Okay, very good. I get 1 plus. Okay, actually, well, not minus, it's plus. So what do I get? I get c to the 4th over 8. Oh, remember there was an 8 in the expansion? You may see it coming out now. Okay, then what do I get? I get the expectation of delta L squared. Right? Okay, so let me write that down. Expectation of delta L squared. So let me in fact write it this way. Let me say it's just the variance of k hat L. right? This is just k hat L minus its mean after all. That's a good way of writing it. Okay. Plus terms that are of order n to the minus 2. Right? Because from the third moment on, my estimates, okay, you don't know how hard I had to fight to get the ceiling to come up. Okay, I didn't want to lose a half power, but they're all integer powers of n. That's the correct order of magnitude. And when q is 3 and above, it's 1 over n squared and lower. Oh, look, that's not too bad at all. It's not too bad at all. And now what do you see? Now you just see that the first term, right, is precisely the expectation of f against the Gaussian measure, in which all the neurons are mean zero, independent Gaussians with variance GL. Oh, that was nice. Okay, but what do I do with the second term? Okay. Well, for the second term, so let me write it and then I'll complete the proof, okay? I go over Rm, get f hat of c, and I get c to the fourth over 8 times, okay, this term, which is now just a constant, the variance of k hat L, times x of minus a half c squared GL c. Okay, very good. So, and again, I'm going to ask for some participation because no fun when you already know the answer. What am I supposed to do? Say again?
By parts.
Nah, yes, integrate by parts. Okay, that sounds good. In fact, I'm going to not even really integrate by parts. I'm just going to say, recall, right, that in the momentum space, Ci, yeah, I'll call it Cj, the j component of C is just like, I have to remember the signs, but it's like minus I d with respect, the derivative with respect to the j component in position space. Right, so in other words, multiplying the Fourier transform by a polynomial just corresponds to a differential operator applied to the original function. Oh, that's great, because then I have some other deformed function that I again integrate against my Gaussian. Well, look, life is pretty good. Life is pretty good. Okay, so I get the expectation with respect to GL of f plus I get the expectation of the variance of k hat L divided by 8. And then I get the expectation GL. Now I have to apply an interesting differential operator, right? The sum of the squares of x's is just like the Laplacian. That's all you do. So you write the sum of j goes from 1 up to m of dzj squared. And I have to square it and apply it to f. And then I have go over the terms. Okay, and the last thing is, okay, you already know that this variance of k hat, I told you, is order 1 over n. And so to leading order in 1 over n, I can replace the g by a k. Okay, I'm skipping that part. But k is like g is k plus order 1 over n corrections. You have to check that if you're being careful. And then you can replace the g down here by a k because you only care about things up to order 1 over n. Okay, beautiful. So my expansion formula is almost done, except now you see that the variance of k hat is going to be the fourth cumulant. Okay, so finally, okay, we have lots of time somehow. Finally, okay, so what do we get? We get KL plus 1, 4 of x. Ooh, wait, no, don't that yet. No, not finally. Not finally, next. Okay, good. Not off that easy, I'm sorry. Okay, KL4 of x. Okay, so let's just remember for 1 second the definition, right? This was like 1/3 of the expectation of ZL1 of x to the 4th, right? Minus 3 times the expectation of ZL1 of x squared. Ah, nice. Okay, that looks like a good definition to me. So but now the point is that, you know, just like when we compute these characteristic functions, you condition on the previous layer. Let's condition on the previous layer in both of these expectations. Okay, so this expectation I'm going to write as the conditional expectation given CL minus 1, and then I'm going to integrate out everything else. Okay, so you get 1/3 of. All right, very good. So this first one, you get the outer expectation, and in the inner expectation, this is just a Gaussian. So it's 3 times k hat L squared, right? That's the variance of a Gaussian after all, or the fourth moment of a Gaussian. It's 3 times the variance squared. Okay, minus 3 times the expectation of k hat L. Right. Oh, look, the 3's cancel. Okay, this is the answer to your question, Domenico. You gotta put the 3's in there, otherwise you are hopelessly unhappy. And what do you get? You simply get the variance of k hat L. Ah, nice. Okay, so the point is, remember, the philosophy is everything is a collective observable if you just look at it the right way. So indeed, like the second cumulant was a collective observable, and the fourth cumulant is just the variance of a collective observable. Everything is mediated by collective observables. Okay, ordered parameters, whatever you want to call them. Okay, so then, yeah.
Okay, assume that you were to go further term in the expansion.
Yes.
Then you get the sixth cumulant. Yes.
Well, so yeah, the next term gives you the sixth cumulant because the third cumulant is the same as the third centered moment. But the fourth term will not be so simple. It will not be the eighth cumulant. It'll be it'll have a correction.
But do you have any tradition for what collective observable this would correspond to?
Yeah, so right, so okay, let me put it this way. The 1 over 2k with this binomial coefficient times the expectation of CL1 of x. 2k. Sorry, that's not what I want to say. The kth cumulant, the 2k cumulant, this is what I want to say. Okay, is simply the kth cumulant of delta L, or I'll call it this way, kappa L. That's fine, right? Okay, the cumulants of one layer, just of these elementary fields, these elementary observable Z, turn into cumulants of.
So the fact that the higher order cumulants themselves go to 0 reflects the fact that the sample covariance has a center limit here.
Exactly. Well, it has a law of large numbers. Yeah, that's exactly that is why it's the same kind of thing. It's just you go further in the expansion, you get more. Okay, it depends how much you want to work to get the constants. Okay, so I haven't yet derived the recursion. I'm trying to think about what to do. I could derive the recursion because I haven't used. So okay, I derived for you the expansion of the expectation of f. That makes me feel good. But I haven't yet derived the recursion in L for the 4-point function for the fourth cumulant. So let me briefly do that. And then what I'd like to do is I'd like to spend the last, 10, 15 minutes trying to explain what are some interesting open problems interactions. I think it's a good way to end some lectures. Okay, but before I erase, let me ask if there are questions. This is great.
More question?
Yeah, of course.
What about that? It's completely generic. It must be
Polynomially bound. That's it. But you just need f hat to be integrable against the Gaussian.
But no smoothness.
No, that's the beauty. Everything. So here, okay, here I wrote it as some local operator against f. But if f isn't smooth, you simply keep the c squared or the c to the fourth over here. You differentiate the Gaussian density and you have a Hermite polynomial. And then it's just the integral of f against the appropriate Hermite polynomial. So again, if it's polynomially bounded, all
generalized derivative.
Yeah, exactly. It's just weak derivatives, but I always mean weak derivatives because it's more convenient. And unless someone is really paying attention, no one's going to ask you. Yeah, other questions or comments? I want to show you briefly how to use this recursion. Okay, now up there. I'm going to erase so people think, hopefully. And you'll see why I needed exactly the form of the perturbative expansion that I got. I really needed a function f that depends on some finite number of neurons. And that's kind of obvious because you saw that the fourth cumulant has this interpretation about correlations between two neurons. So you know it's not going to be something that only knows about the marginal distribution of one neuron. That'd be too good to be true. or too bad to be true. I don't really know. Okay, let me. All right, very good. So now I get to say finally. So here I really won't do every step. I promise it's like a little bit of algebra. Okay, so here's the game. So you have the kappa L plus 1 for x. I wanted to derive a recursion for it. Okay, so the first thing is kappa L plus 1 for x is just the variance of k hat L plus 1, right? That's what I just said. So in fact, let me go back and just write it as the expectation of delta L plus 1 squared. I'm going to write it in this way. Okay, well, okay. So I'm already about to declare victory. Okay, it doesn't look like I'm close to victory, but victory is always around the corner. Okay, so defeat. I feel bad. Okay, but the point is that you see delta L plus 1. Okay, where's my formula? Okay, I erased the formula. So, but delta L plus 1 is a sum over things in layer L. Remember, I'm going to write this formula for you now. But the point is that okay, let me go back to emphasize this. The variance of k hat L plus 1. And this is the variance, right, of CB plus CW times, CW over NL times the norm of sigma L of x, sigma of ZL of x. Split. Right, that was our that's the formula we had for K. And you see the cumulants at layer L plus 1 become variances of collective observables at the previous layer. That's why you're about to get a recursion. Okay, so moreover, let me write it this way. This is the variance. Okay, you can kill the constant CD. That's not very exciting, right? Because you can always shift by a constant. So you get CW over NL, and let me write it explicitly. The sum on J goes from 1 up to NL of what? Okay, I get sigma of the CLJ of x squared. Okay, I'm sorry to tell you what the squared norm of a vector is, but I have to do it. Okay, very good. But now, what do you know about such an object? Right? The variance of the sum is the sum over all the covariances. Okay, very strong. So what do you get? So you get CW over NL. Okay, so you get CW squared, over NL squared, and I have a term which corresponds to the diagonal. So I'm just going to compute the variance of the first one, CL1 of x squared. Right? That's when you take the double sum over the covariances and J1 equals J2, so to speak. Okay, plus you get CW squared times the off-diagonal terms of the sum. That's how many they contribute after normalization, right? You get a 1 over n squared, and there's n times n minus 1 terms off the diagonal. And you get the covariance between sigma of CL1 of x squared and sigma of CL2 of x. All right. Well, that's not too bad. It's not too bad. Not too bad at all, in fact, I would say. Because what? Well, okay, so first of all, you see, this first term here, this is some function f that has to do with just a finite number of neurons. I already have a 1 over n in front of it. And so I can just apply my perturbative expansion to it. So I get CW squared over NL times, okay, I'm supposed to write the expectation with respect to GL of this thing. ZL1 of x squared. But again, I already have a 1 over n. So I'm going to replace it by a k because I'm okay dropping terms of order 1 over n squared. Okay, plus, well, okay, now I actually have to do this. Okay, so I have to do CW squared times 1 minus 1 over NL. And now so you see here now, when I write this as the expectation of the product minus the product of the expectations, I have some function f which depends on 2 neurons. Well, okay, my formula works for any finite number of neurons. 2 is finite, last I checked. Okay, so I have to write this as the expectation of sigma of ZL1 of x sigma of CL2 of x squared minus, this way, the expectation of the product. Sorry, the product of the expectation. They're the same. Okay, so let me just leave it at this. Okay, I promise now when you go through and you apply this formula, the fact that this term here was kappa L4 of x is going to give rise to kappa L4 of x in the second term. And this term here is just transparently going to give you the variance of sigma. Yeah. No, what did I do? Oh my God. Ah. Sorry. So the variance. I don't know why I put the expectations. Right. This is going to give you the variance of sigma squared in the infinite width limit. Very nice. You already have that. And now this term is the other. So you just applied the recursion. Okay. So that's the end of the proof. That's all sort of what I want to say about it. I promise it's just a little bit of algebra from there and some head scratching to make sure that you trip through in various places. Okay. So there's a little bit of time left, but let me stop and ask if there are questions or comments on any of this, because I'd like to, I think, skip tuning to criticality and just talk about open problems, maybe. That's the right thing to do. Questions or comments about this? So I'm sorry, I had to erase the statement of the theorem because I had twice as many boards. Right? I can always complain. So let me talk about open problems. So I've tried to present like what I think is a pretty coherent set of techniques that allows you to investigate at least random neural networks, and then sometimes you can say things about trained networks too, depending on how hard you're willing to work. And I can't remember who asked me this question, but it was a great question. The point is that these techniques don't depend too much on the architecture you chose. You can change the structure of the forward pass, and it just changes the transition matrices or the transition probabilities in your Markov chain. And you have to just redo the analysis. But then on the level of the neural network, something new and exciting can come up depending on the setting. Okay, so let me say some of the open problems. So as an obvious preface, okay, this is like very non-exhaustive. I have a million questions. Like I've only talked about a measure zero set of things people think about with neural networks. And even this is going to be a measure zero set of my measure zero set of things you can think about doing. But okay. So let me start kind of like this. I tried to convince you a little bit that this L over N measures the rate of convergence to the Gaussian process, but I was a little vague. My notion of Gaussianity was like how small is the port cumulus? Okay, that's something, but it's not everything. So sharp, okay, with respect to the depth L, rates of convergence. Convergence to the Gaussian process limit. Okay, so yeah, like it should be true that in your favorite metric, things are like L over N, but actually it's more complicated than that, as you'll find out if you either ask me or read some papers or whatever. So like the general conjecture, so it's kind of like in the linear networks. It should be something like exponential in L over N. Roughly like L over N minus 1. Something like this. Okay, when L over N goes to 0, the distance goes to 0. When L over N grows, you're very far from Gaussian. That's my best conjecture. I can prove this for ReLU networks at a single input. Okay, whatever. I have some reason to make a conjecture like this. There should be a constant here.
So the leading order is L over N, not the square root of L over N. In your conjecture.
Well, okay, I haven't told you if it's like what exactly I'm measuring, of course. But somehow like what I'm saying is the dependence on L over N should be exponential. I don't know what else to say. Like maybe it should be like this, depending on which kind of distance function. Maybe I wrote a squared distance. I'm not being very precise, but that's kind of my point. Okay, maybe definitely open, and actually like would have some interesting consequences. So but let me say it in a slightly different way. Part of my motivation for doing this, and really a lot of the things I presented to you, is I've said this a couple of times, but it's called deep learning, and depth is supposed to be important, right? Back whatever in the 80s, 90s, we mainly used one layer networks, and we know today that deep is important to some extent. And but still, the actual importance of depth is not well understood. I'm trying to outline some part of the importance of depth. You need deep so that you can be not Gaussian and you can have correlations, you can learn features. I didn't state the theorems about the features, but there are sort of extensions of what I did, said things around feature learning. But we don't really understand what's going on. And it's clearly a crucial thing to understand. So anything you can say that's sharp surely will be interesting. Okay, so let me tell you my personal favorite problem, not favorite, but it's one of the problems that been bothering me. And I purposely didn't tell you about it, I think, because I thought I'd show it to you here. Okay, very good. So compute the Lipschitz constant. Of a random rel now. It's a surprisingly easy problem and actually important for various things in practice. You start training. Okay, ideally you prove it after training too, but let's start at the beginning of training. You start your training with some function that you guessed. And the Lipschitz constant is just how big are the derivatives of function piecewise linear. I want to know what's the soup of the norm of the gradient of my function. Done. Okay, we don't know. There are no good estimates. It's pretty sad. It's pretty sad. I think the best I know how to do, I can say something about input dimension 1. That's pretty sad. Okay, I think I can give the right answer in input dimension 1, but no one uses one-dimensional data in the real world. So here you go. But in a more serious way, I mentioned very briefly at the beginning of the lectures these adversarial examples. The adversarial examples are all about the statement that even after training, networks are highly sensitive to changes in the inputs. Okay, you give yourself something that's obviously a car, and somebody can go and slightly change some pixels on the car. So to a human, you can't really tell the difference. It'll totally change the output, the prediction that you get in the network. So it's really a question about the Lipschitz constant. You can think about it this way. And indeed, there's a series of papers that tries to understand adversarial examples in randomly initialized value networks. It tries to basically take the point of view of these papers that, okay, if you believe that adversarial examples are always there, which we typically observe in practice, maybe they're so generic you can understand them at the start of training. And they prove in various horrible and less horrible ways that at the start of training, there's often adversarial examples. You choose an input, and there's a surprisingly small distance you can go to flip the sign of the output, that kind of thing. It's kind of beautiful and interesting in some way. Okay, so fine. So these are really questions that are maybe closer to the Gaussian, or interesting, let me say, in the infinite width limit. How about that? I think those are interesting things. In the strict infinite width limit, there are ways to bound the sup norm of a Gaussian process. I get some Gaussian process. I'm just asking for an L infinity norm on the gradient of the Gaussian process, so you can say things. But so it's interesting to say things at finite width and to understand the difference between finite width and infinite width. So question number 3 are scaling limits of neural networks as n and L both go to infinity at a fixed ratio. Okay, I call it beta. Turns out if you are like a statistical physics person, at least for value networks, you can think of L over n as a kind of inverse temperature. There's really an interpretation of it. That's why everything's exponential in L over n. And at least for value networks, like I said, there's some there are things called random polymers, and they have their own partition functions. And it's really some okay, at least vague analogy, but it's kind of interesting enough. And let me just be a little vague and say that typically, if you really want to study what the whole network does, what people have realized is that you can't take a fixed nonlinearity. You have to take a nonlinearity, which is the identity plus a small perturbation, usually something like constant over square root of that. Basically, what happens is if you have too much nonlinearity in each layer, things will become more and more and more and more correlated, and you won't get a very interesting scaling. Okay, but there are things called residual networks, for example, that basically do this kind of thing. Okay, in each layer, they approximate the layer as the identity plus a small correction, or potentially small correction. And so I'm being a little vague, but I just want to be honest. The really interesting scaling limits, and there's a kind of a beautiful paper that explains like an SDE that the covariance, this kappa, or this KL plus 1 that I was writing down satisfies, can really be thought of in some interesting like PD kind of way. Okay, so basically very little is known about these scaling limits. Even really the existence of a scaling limit that depends only on beta. In general, it's just not known. In particular, you could ask what happens to learning, what features do you learn, okay, blah, blah, blah. You can ask every question under the sun. Okay, so let me now say something else about these scaling limits, which for me is actually like a really exciting question, I think. Okay, so you take sigma of t to be the identity, and you do the same thing. You take CB equals 0, CW equals 1, what I started with these matrix products. Okay, I'll rescale L to L plus 1. Okay, so you have to see L is just the product of L matrices. And so here's a crazy statement, okay? Believe it or not, in the limit where n and L both go to infinity, and the W's are just products of independent Gaussian matrices, okay? I was the first person, okay, like 2 years ago, to actually compute the global, like, empirical distribution of singular values. Okay, like, in some sense, the most classical question in random matrix theory is you give yourself a random matrix, what do the eigenvalues look like? What do the singular values look like if it's not symmetric? And like a bajillion million papers, like I said, have been written in the two regimes that I sort of outlined where L is fixed or N is fixed. But if you send both of them to infinity, we didn't know what the distribution of singular values is. Okay, now we know. But that's only for the Gaussian case. Okay, that's pretty sad. And still the universality is open. Almost everything is open. Local statistics are open. Okay, so in this case, so take L over N to a constant beta, okay, and study the spectrum. I'll write it that way. Okay, whatever your favorite notion of studying the spectrum means. If you want to study the level spacings, go for it. If you want to study something about the eigenvectors, okay, I don't know.
What kind of results one gets? I mean, what is the relationship with classical results like Wigner's law or Markov's rule or whatever?
Okay, I have plenty of time, so let me tell you. Here's what happens. So I don't know if you'll be excited or disappointed, but okay, here it is. So here's two things you can do. Let me explain it this way. Okay, you can fix L and you can send N to infinity. And you get something which is called the quarter circle law, okay, when L equals 1 at least. It's like the entropy maximizing thing, blah, blah, blah. Okay. You get some particular quarter circle law. I'll call it mu1. That's like the empirical distribution of the singular values is something beautiful and nice that you can describe. Okay, and then you can take the same thing and get mu2, you can get mu3 and so on. And in free probability, there's the notion of multiplicative free convolution, which tells you that mu2 is just the multiplicative free convolution of mu1 with itself. Okay, there's the analog of the sum of random variables have convolution structure. There's a multiplicative convolution on the spectrum. Okay, so there's some beautiful sequence of operations like this.
One mu2 is really in correspondence of L equal to 1 L.
Precisely. And when you take L to infinity, here's what you get. Okay, if you study the squared singular values, okay, so here I should be precise. You study the spectrum, so that I can rely on tape, so to speak, to the 2 over L power. That's the thing that keeps the spectrum bounded. What you have to do. Spectrum here means singular values for me. These are not symmetric matrices. Okay, they converge to the uniform distribution on 0, 1. That's what happens. You have a sequence of measures, and their weak limit is uniform distribution on 0, 1. Very nice. Okay, now you can do the opposite. You can fix N, let L go to infinity, and the multiplicative ergodic theorem, so I'll call this nu sub 1, okay, says that you get your one singular value here converges to an almost sure limit. Okay, and then you get a different nu sub 2, your two singular values, or to the opposite exponents, but I'll talk about it, singular values, converge to some limit. And in this way, you can take the limit of these atomic measures as n grows. Okay, you can ask what's the weak limit of these things. Okay, and what you get is the uniform distribution on 0, 1. So Okay, now you can guess the answer. So it turns out you get the uniform distribution on 0, 1, no matter how you approach. So as long as n and L both go to infinity, you always get the same thing. And there's some deep reason why this is supposed to be true. Like, okay, it's going to be very esoteric, but I'll say it anyway. So the uniform distribution on 0, 1, you're supposed to think like this. You're supposed to think of L over n as being a time parameter. This is time equals 0. This is time equals infinity. So n over L is a time parameter. Okay, and the dynamics that you get, and this is a conjecture, people still don't know how to prove this for sure. The dynamics you get as you increase time, in other words, as you make n bigger relative to L, is exactly that of what's called a Dyson-Brownian motion. There's some beautiful classical interacting particle system. Okay, and this is the initial condition for your Dyson-Brownian motion, uniformly spaced points. Okay, so there's a theorem, not too hard to see, that the uniform distribution is an invariant measure for the Dyson-Brownian motion. And that's why the global distribution of singular values is always the same, an invariant measure for the dynamics you get. However, the conjecture, which goes back to Percy Deift and people like that, is that any local statistic, whenever you do anything like zoom into the bulk of the spectrum, you're going to get an answer that depends on the value of t. Okay, so for example, the largest singular value, S1, over here has a Tracy-Whittem distribution. Actually, everywhere here has a Tracy-Whittem distribution. When you normalize, okay, I'll write S1 to the 2 over L. It's kind of a beautiful thing. It's like the rightmost particle always has Tracy-Whittem. And over here, S1, the 2 over L, looks like e to the Gaussian. So you have a very interesting transition, which is not fully understood really at all. Okay, so there's lots of, like, I'm just saying, there's not the pure random matrix questions that people could study. You don't have to care about neural networks at all. That's just how I got into the questions. Okay, very good. Okay, I have negative 50 seconds, but I'm going to still write one more thing. Nice. So I wanted to mention at least one more class of problems. Okay, so like I told you that you can study optimization when you're in the linear regime, because optimization is just that of a linear model. But of course, then I immediately told you that I don't care much about that regime and I want to study nonlinear. Okay, but we understand very little about it. Okay, so any kind of quantitative, maybe, okay. What can you say? Results on this, right? So like, let's say either the final layer activations that you get when you do dynamics on theta. So you start training your network and you ask, what do the final layer features look like? Okay, maybe I'll say sigma of these things. Okay, these are the things over which you have a linear model. You want to know that? This is what people sometimes call the features. So when t is large, I want to understand what happens at the training network. Or maybe you care about the NTK. What does a neural network see when it actually does optimization? How is it adapting the geometry of like the space in which it's doing optimization, which was captured by the linearization of your model? Again, when t is big. Okay, we have very little information about these things. It's crazy. And like this is definitely like, a great thing to understand. Okay, so let me stop. I'm already 2 minutes over. That's all I should say.